Hello there. If you didn't get a chance to see my first two videos in the calculus series, an overview of calculus and the tangent line problem, please do check them out as they set the stage for all that follows, in particular introducing how the concept of a limit is so essential to the study of calculus. In this lesson, we begin our study of limits in earnest, focusing on definitions, notation, and proper math speak. Thank you for watching.
So let's consider the following function to help introduce us to the concept of a limit. F of x equals x squared minus 1 over x minus 1. Now, you will recall from pre-calculus and maybe even algebra 2 trig that it's very helpful to analyze the domain of a function, and we know that the denominator cannot be 0. So let's start with that. We want to make sure that's not equal to 0, which in essence is saying that x cannot equal 1. What would happen if we put 1 in for x? Let's just look a little closely here because it's a curious situation. We actually get 0 over 0, which is a little different from if we had got 5 over 0, we would have said the answer is undefined. In this case, we say the answer is indeterminate. And indeterminate, I will use that word again moving forward. And what that translates to in a graph of this function, well, here's a graph from Desmos. Now, in this graph from Desmos, it doesn't actually look like there's any problems with x equals 1. It seems like all is well there. But we know already that x cannot equal 1. Something is going on here. And what that is, if you recall from pre-calculus, is that we actually should have a hole here. So if I just type this function into Desmos, it's not really going to pick up that little detail, which is why it's so important to be able to analyze a function. So I'm taking the same function and I went back into Desmos and put the hole in where we know it should be at 1, 2. And I'm also going to incorporate a table of values so that we can understand the behavior of this function as x approaches 1. So what do we notice? As x gets very close to 1, f of x, aka y, gets very close to the value 2. So we can see this in the graph. So as we're coming along the graph and our x coordinates approaching 1, our y coordinates approaching 2 from either direction. In case you don't trust that, let's have a look at the table. As the x values get closer and closer to 1, the y values get closer and closer to 2. So we have like just 1.999 on one side of x equals 1 and 2.001 on the other side. You can sense that they're converging to the number 2. Notice that at x equals 1, if we plug in x equals 1, we get an error as we expected from our analysis before. So how do we put this into math speak? So this is now where we formally get into an understanding of limits. We say the limit of f of x as x approaches 1 equals 2. So we're not saying that f of 1 equals 2 because it doesn't exist. But we're saying that the limit of the y values as x approaches 1 is getting closer to 2. And in math notation, we write this in a special way. So we write limit as x goes to 1 of f of x. So that first part says the limit as x goes to 1 of f of x. Apologies, my m sort of looks strange. There we go. Limit of f of x as x goes to 1 equals 2. And that's our first limit statement. Now let's change the function up ever so slightly. So notice that g of x, the only thing I've added is an absolute. I took f of x and I took the numerator and I put an absolute value over the numerator. And this creates for an interesting looking graph. So where before I had basically a straight line with a hole at 1, 2, I now have caused a kind of break in the graph. And let's look at the table. to kind of, have both ways of inspecting this function. And what do we notice now? As x gets very close to 1, that's always how you preface the concept of a limit. As x approaches a particular value, what's happening to y? Where is y tending towards? Well, as you can see, or in this case, g of x, is not actually getting closer to any one particular value. In fact, if we approach, let's do what we did before. As we get closer and closer to 1 branch of the function is heading towards a y value of -2, and the other branch of the function is heading towards 2. And you see that in the table as well. As x gets closer to 1 from approaching from the left, y is getting closer to -2. It's not actually equal to -2 here. This is some rounding error, rounding that rounds it to -2. It's probably -1.99999. As before, there's still an error at x equals 1. We've got a problem with the function right there. And on the other side, as x approaches 1 from the right, we are approaching +2 this time, not -2. So in math speak, we say the limit of g of x as x approaches 1 does not exist in this scenario. And in math notation, we write, so the limit of g of x as x approaches 1, since there's no kind of one fixed number that the y values are approaching, we say that this limit does not exist. So this brings us to a definition of a limit, kind of semi-formal definition. There are more formal ones that involve deltas and epsilons, but we don't need to do that for this course. So we say that the limit of f of x as x goes to a is equal to L. It exists and it's equal to L if we can make the values of f of x arbitrarily close to L, i.e. as close to L as we like, by controlling the values of x. So if we can make x sufficiently close to but not equal to a, either on either side of a, as x gets closer and closer to a, if f gets closer and closer to a finite value L, the limit exists. So let's do just a couple diagrams to help us visualize this. So we could have the situation we were just looking at before. So we could have a curve with a hole in it. And if we mark this as a and L, so as x approaches a, the y values approach L. That's pretty straightforward. That's where the y values are heading. But not to be certain there's no confusion. This limit is still L. So the limit of this function is still L, even if the function actually exists at a. So say f of a actually exists. It's not equal to the value of L, but it does exist. The limit still stands. The limit is still L. And then there's one other scenario which is easy to overlook because it feels like there's nothing really going on here. But say there's no hole at A. So f of A actually exists. It's actually equal to the value, whatever the value L is. So the limit still exists. Even it's just very easy to overlook that. So important to see that one situation as well. So the functions we looked at just on the slide prior were kind of very straightforward and not hard to see that the limit exists. But let's look at a more interesting function to get us a deeper appreciation of limits. So let's look at this function. So if x is a rational number, y is just equal to the value of x. So what are rational numbers? That would be like x is a half, any number that can be written as a fraction. So half comma half. X could be an integer, so -1. That could be written as a fraction, so -1, -1. A repeating or terminating decimal, so 0.6, 0.6 repeating. And even x equals 0 is considered rational. So those are points. Those are some of the points on this graph. What about irrational numbers? Irrational numbers would be something like the square root of 2, which is neither repeats nor terminating decimal. And even pi is irrational, so therefore pi over 10 is irrational. Pi over 10 comma 0. So you can imagine, pick any irrational number for x, and the y value is going to be 0. So hopefully you can envision this emerging. And this is a graph it's pockmarked, tons of holes and gaps, and it's sort of composed of two components. Any value, anything along the line y equals x is has an x value that's irrational. Not irrational, a rational number, so half comma half. And anything along the line y equals 0 has an x coordinate that's irrational. So for example, pi over 10 is 0.314 ... So it's somewhere around here. So this would be pi over 10 comma 0. So we want to think a little bit, does the limit exist on this graph anywhere? And I'm going to pose to you that it does exist in one place. As x approaches 0, the limit of h of x exists. And based on our definition from the slide before, we have to think about, as x gets closer to 0, what's happening to our y values? Well, you can see that as x gets really close to 0, so if x is irrational close to 0, then y is 0. And if x, so we're approaching along here towards 0, and if x happens to be rational, the y value is still approaching 0. So if you remember the definition from before, so I'm posing that the limit as x goes to 0 of h is 0. From the definition before, the idea was that if you can get arbitrarily close to 0 by choosing x appropriately. So say I wanted to see, can h be 0.0001? That's really close to 0. Well, yes, it can. If I just make x 0.001, I've delivered you very close, your y value very close to 0. And if, in fact, I want to get even closer. So say I wanted to do 1 times 10 to the minus 20. Well, just give you 1 times 10 to the minus 20 as an x value. And you are getting closer and closer to 0. In fact, if I just then go and pick an irrational number, any irrational number that's really close to 0, I also get 0. Apologies for this little squiggle. Okay, so that limit, I think we can see that limit exists, but what about another limit? What about as x goes to pi over 10? So again, we know the point pi over 10, 0 exists, but if we choose an x value close to pi over 10, say 3.1, so 0.314. Well, 0.314 terminating is a terminating decimal, and so its y value would also be 0.314. So as we see, as x gets closer and closer to pi over 10, I'm going to be oscillating, my y values will be oscillating between 0 and something very close to pi over 10. And because there's no fixed y value that I'm tending towards, we say in this case, the limit does not exist. In fact, the limit does not exist for this function for any other value save x as x approaches 0. So this is the only limit that exists.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.